Well, good morning, good afternoon, good evening, and almost good night for those of you in inconvenient time zones like our speaker. It gives me great pleasure to start this Wednesday EMinar, and today it's lovely that we have Graham Heinson, who's done us all a favor by staying up late so that most of us can get to watch him. But before I introduce Graham, let me just remind you, you can go onto the EMinar webpage on MTNet, and there you'll find previous recordings and presentations that you can download, both season 1 and season 2, and you can see registration links for upcoming webinars. Just a quick reminder, you're on a webinar, which means that you have a raise hand function. So towards the end of the talk, if you want to speak, if you want to speak, just, oh dear, I'm losing track. If you want to speak, just raise your hand. Otherwise, you can put a question in the Q&A. And I ask you to put questions in the Q&A, please, rather than in the chat. So Graham's going to talk to us on scale reduction MT studies to link deep source regions to deposit scales for IOCG and AU deposits in Australia. And you know, unless you've been living on Mars, you'll know the tremendous successes that the MT groups have been having in Australia, looking beneath the regolith, and it's absolutely tremendous. So Graham, most of you might be aware, Graham's a professor of geophysics at the University of Adelaide. His group runs the national pool of MT instruments funded by OSCOPE. OSCOPE is part of a large initiative called Uncover, and I believe it's $200 million initiative to cover Australia with MT and airborne EM and seismics. And OSCOPE is a component of that, and it's been used in his years from the top kilometre to the lower mantle and from the Antarctic to Greenland. He's currently thinking about doing geophysical surveys on the moon and the Mars. Well, perhaps you could get some very rich billionaire to help you fund that, Graham. So I'll stop sharing and hand over to you.
Thank you very much, Alan. I will start my share of my screen, and hopefully you can all see this now.
Yeah,
it's a good. Excellent. Thanks, Alan. And thank you for that generous introduction. It's a great pleasure to be presenting today to the wider MT community. And I think this seminar series that Alan and colleagues have set up is just a phenomenal resource. Alan and I were just reflecting a little bit on this and how great this is for future students. Before I get started on the talk, I'll just pay acknowledgements to the Kaurna people, the traditional owners of the land that I'm giving this talk on at the moment, and I pay my respects to their elders, past, present, and emerging. So what I'm going to talk about today, and I've listed my co-authors and partners in crime, and these are a few of them that I interact with, obviously, pretty much every day, but there's a much wider community within the Australian MT circle. Over probably the last decade, but maybe a little bit longer, we've been very much thinking about how MT can be applied to exploration problems, and particularly mineral exploration. And rather than sort of seeing MT as being a technique to just detect the deposits themselves, is to try and think about the whole mineral system. So at the bottom, I've got numerous sponsors, and there are many others involved, but you can see the main ones there. Okay, so what I'm going to do in this talk, I've structured it like a movie. I've split it up into 3 acts. So most movies, most films break up their narrative into these sort of 3 sections: the setup, Act 1, confrontation, Act 2, and resolution, Act 3. You can see the various touch points within that cycle, going from sort of the introduction to the point, the twists in the plot, and then the disaster and crisis at the end of Act 2, and then the sort of resolution. And we can recognize that from many, many movies that we've seen over the years. So I'm structuring my talk in the same way. So I'm going to move on. This is Act 1. So this is setup. Now, this is a beautiful picture. You can make out in the yellow high-vis top, that's Kate Robertson putting out an induction coil. The other person is Sam Jennings setting up the LEMI instruments. This is putting a broadband instrument out in the Curnamona Province in the middle of Australia. You can see a typical landscape of Australia. It's kind of almost barren of vegetation, very flat, and the helicopter's just in the shadows here because access is a real issue in many parts of the country. So what I want to do, though, is to not talk about MT to start with, but talk about the motivation for thinking about how you'd use MT for exploration and why we would want to use it. So this is my first slide, and it's basically the demand for copper. Now, on the left-hand side, I've just got some statistics about if we turned all the cars in the UK from hydrocarbon into EV, you need a phenomenal amount of metals, and particularly copper, but also the various rare earth and sort of critical minerals. And the stats are essentially that the amount that's required will be staggering if we are undergoing this green technology revolution. And our esteemed leaders are currently in Glasgow at the moment, sort of talking about these technology advances that will, we hope and pray that will make the world a better place. So this figure on the bottom basically shows the demand for copper, and the forecast for the demand for copper is that we will use more copper in the next 20 odd years than we've used in the entire history of the planet. Now, some of that will obviously be recycled, but a lot of that will have to be new copper. So there's a huge demand for minerals, particularly the metals like copper, but also the rare earth elements that often accompany copper deposits. Now, in Australia and globally, we have cycles in the mineral industry, and they go up and down. We're in a slight rise at the moment. We're actually seeing a lot more investment in gold and base metals. It's a long way down from its peak of about $5 billion in about 2012, when I think I was hosting the Darwin EM workshop. That was more or less the peak, and that was largely driven by iron ore and coal. And subsequent to that, that's rapidly decreased, but so we're about half of what we were at that point, and there are cycles within that. So companies are spending more money on exploration, but the success rate is diminishing quite significantly. So this supposedly shows the number of discoveries in Australia over the last 30 years. The yellows are the gold, greens are base metals, and other metals like iron ore are included in bulk. So you can see that the greens, the base metals, things like copper and gold, have sort of come and gone a bit. The big rise was in iron ore and coal in the last about a decade ago. But in the last 2 or 3 years, there's been almost no discoveries. So despite all the extra expenditure, we're seeing very little in the way of extra discovery of mineral systems. And that is in the context of the big requirements that we have to find more copper and rare earths and critical minerals to fuel the green technologies that we need. So this is another way of looking at it. This is the amount of money you need to spend to find copper. So the red line on here says that if you spend $1 billion in US dollars, and this is in 2016, then you are likely on average across the globe to find a sort of a tier 2 deposit, which has a sort of somewhere between 1 and 10 million tons of copper equivalent, which is way less than was required for all the expansion of industry. So if we wanted to find mineral systems and mineral deposits of the size of Escondida, the largest, you'd need to spend something like overall about 50, 60 billion dollars is the type of expenditure required to find a mineral system of that size, and that's the sort of the average. So you can obviously find more tier 3 deposits, but very few tier 1 deposits. And it's really the tier 1 deposits, the ones that produce the most metals, and therefore for the companies the most profits. So in Australia, this is the last few years. It only goes up to 2016, but nothing much has changed because very few things have been found in the last few years. There's been no tier 1 discoveries in the last decade. Relatively few tier 2 and relatively few tier 3 deposits. And that's the sort of distribution of those types of deposits. So it's a combination of copper, gold, iron. And a large reason for that is because most of Australia is covered. Alan alluded to the regolith cover of Australia. Australia is essentially a very flattish country, large deposition of sediments, both in situ, deposited and weathered, and also transported. The map on the left shows the depth to basement. So the lighter browner colors are where the basement rocks are near the surface. So you can see those in Western Australia in the Yilgarn province. And the bluer regions are the deeper sedimentary basins. But overall, even in those areas which have relatively little cover, there's still tens of meters perhaps between the surface and the basement rocks. And if I plot and show where those mineral systems have been found, they've all been found in areas with minimal cover. So the ones in WA are largely in the Yilgarn province and in the Pilbara. We've got some mineral sands in South Australia and a combination of coal and some base metals in Queensland. So for much of the country, we're not discovering mineral deposits. And those mineral deposits are gradually getting harder to find, and where they are found, they're becoming deeper. So this plot, many of these plots I'm showing from a company called Mineral Exploration Consulting. I've referenced those in the slides. You can see that sort of the depth versus the age, and there's a kind of vaguish correlation, but and some of those deep gold mines are obviously in South Africa. But overall, the trend is for deeper mines for hundreds of meters or even kilometers. So some of the very deep iron oxide copper gold deposits, which are currently being developed in South Australia, for example, are well over 600 meters deep and in some cases up to 1 kilometer deep. Okay, so exploration for mineral deposits, and to find that particular deposit, which really, when you think about mineral deposits, they're essentially just concentrations of a chemical element. So it's an excess of copper or iron ore or whatever the commodity over and above what you would expect from normal crustal abundances. So the actual ore deposit itself, the one which is economic and mined, is tiny. It's a small deposit compared to the size of the country. So that's my needle analogy. Now, the whole system, though, which involves basically the driving of those elements from the deeper part of the earth, and that's both lower crust and mantle, up into the upper crustal depositional space, and then dispersion based on fluids and movement through the regolith. They expand the radius a little bit. And if you take the whole system from the deep part of the fluid system to the regolith cover and dispersion, we can characterize that as a mineral system. And I've taken this figure from John Ronsky from Western Australia. The figure on the right shows a kind of conceptual model of that geochemical flux. You start off at the bottom, and we're thinking in this scale of being lithospheric. So this could be deep crust, it could be the mantle. And that's the primary source of those metal ions. We need something to drive that flux, and a fluid or melt that moves upwards into the crust, and at some point perhaps develops a reservoir it concentrates, and then perhaps through smaller scale fluxes in fractured rock in the more brittle part of the crust, we end up producing a deposit. Now, that's what we call a regional to camp to deposit scale. And you can think of it essentially being lithosphere to camp to essentially the crustal scale in the middle to the deposit scale, which is really the exploration scale in a sort of typical sense. And Cam McQuaig and John Ronsky in their paper in 2014 basically said the pathway to mapping a mineral system is first of all to understand the architecture. So geophysics plays the role here in terms of defining the structure. And then once we know the architecture, we can then think about the chemical transfer. So in the talk today, I'm going to basically do the middle part of my talk, which is Act 2, is about map architecture. And then Act 3 is about the chemistry mapping onto that architecture and a few thoughts in that direction. So when we think about mineral systems, we think about the whole crustal mantle interactions, including the very deep thermal inputs from things like mantle plumes and subduction, and where slabs break off, and the stenospheric upwelling and changes that can drive a thermal regime that can either produce melt, depending on the hydration state, and it can produce buoyant fluids that will move up through the system and up towards the surface. So in quite an important paper, which I'd like to reference here by Bill Griffin, Graham Begg, and Suzanne O'Reilly, basically said to understand a lithospheric mineral system, we really need to think about all of the processes and how they interact to produce the mineral deposit at the surface. So the mineral deposit is the final sink, it's the final part of the mineral system, and it's only a tiny fraction of that system. So looking for that is the needle, but looking for the whole thing is the haystack. So the suggestion I put out here, and this is one I've put out before, but it's a very nice analogy, is instead of looking for the needle, we really need to look essentially for the haystack, for the whole thing. The needle is tiny and it looks like all the other bits of straw again. If we're lucky, a little magnetometer might find it, but we're much better off trying to find where the haystacks are in our environment, which really most of the Earth is not haystacks at all. There is no mineral systems in most part of the Earth. So that's the end of Act 1. That's defining the problem, defining the motivation. Let's move on a little bit to defining what we do about it. So this is Act 2, the confrontation. Another nice picture here of Sam and Kate's. This is a Phoenix instrument in the foothills of the Flinders Ranges. And I talked about my research going on to the Moon and Mars. You can see that much of Australia already looks like the Moon and Mars anyway, so we're not that far away. Okay, so Act 2. What is it we need to do? Well, we need to characterize the lithospheric architecture. This is a really nice figure that Graham Begg put together and basically characterized it from the left, which is the terrain or the regional scale. So this is the big scale, lithospheric sort of scale, to the right, which is the deposit scale, the detection scale, and the middle bit, the orange colors, are the regional or the camp scale. So they're the sort of crustal scale. And the linking kind of aspect of this, I mean, of course, lots of geophysics characterizes all parts of the Earth and has different resolutions and different sensitivities, of course, but MT plays this wonderful role where we go from the long period through the broadband to AMT, going from scale lengths of hundreds of kilometers to scale lengths of tens of meters or less. So it's a very beautiful technique, and we're all converts, so I don't need to preach to you about the wonders of MT, but of course this is a technique that spans all these bandwidths, and our field and our source field is naturally occurring, so it's a fabulous technique to map the Earth with as much detail as we can afford in terms of sites and access and so on. A lot of exploration historically has been focused on the reds on the right. So it's basically trying to figure out where a deposit lies within a complex structural boundaries and essentially geared towards refining drill targets. But what I'm proposing, and I guess what's been proposed for many years now by people like Graham and by John Ronsky and others, is that we really need to start at the left and talk about the whole architecture before we can reach the right. So we are looking for a needle in a haystack. We're looking for the haystack, and we can use MT to map the entire architecture of that haystack. But the other component of this architecture is that although the MT gives you the resistivity as a structural bounds and structural complexity, it also has this sensitivity to chemistry. And that sensitivity to chemistry and the fluid systems that generated that chemical change and distribution means that we have another insight into the Earth, and we can move down the right-hand side of this slide and look at the map of the chemistry onto the architecture. Okay, so look, that's the big picture. Hopefully everyone knows a little bit about the OSLAMP program. The OSLAMP program is been running now for almost about 7 or 8 years. It's a map of the Australian lithosphere in terms of MT calculated or collected at sites, half a degree in spacing, so it's about 50 odd kilometers. It's about 3,000 sites that covers the entire continent. So at the moment, we are about 50%, a little under 50% completed. There's a very large part of Western Australia that has had nothing or very little. But of the states that have been completed, South Australia, New South Wales, Victoria, Tasmania, most of the Northern Territory, quite a bit of Queensland now, have all been completed. And this is a massive collaboration between Geoscience Australia, all the state and territory geological surveys, and the various universities involved. So this is one of my favorite projects because it's coming up with huge changes in ideas and changes in paradigms. So I have this figure. This is slightly an old figure that Kate put together. And of course, it doesn't include the New South Wales and many of the Northern Territories sites, but what it does do is it just plots out induction arrows, real induction arrows, 1,000 seconds. They are reversed in the Parkinson convention. So they point away from resistors towards conductors. And you can see these pin cushion effects in the Gawler craton, which is the bit which, if I just put, and I will get a spotlight, the bit around here, the middle of the Gawler craton, they all point out. There's some bits they all point together. There are some bits where there's a large sort of, if it looks like a flow of arrows, and then from the Musgraves, they all point out. So this maps the tectonic units. And what I'm doing in this talk today is showing you some 3 focus areas. There's an area on the side of South Australia. This, so just to give you bearings, where I've got the pointer, that's Adelaide, that's where I am now. About 3 hours drive north, 300 kilometers. The box on the left-hand side is the Stuart Shelf and includes the massive Olympic Dam deposit. Carapatina is another very large IOCG deposit, and several smaller ones. The box at the bottom is orogenic gold. So this is the Victorian goldfields. And the box that I've got on the eastern side here is called the Curnamona Province. And this is very much a greenfields case, but it has a lot of similarities to IOCG systems. So Kate's produced another lovely figure here, which has phase tensors, again, 1 period, 100 seconds in this case. And what I would have done if I'd had enough time is put the New South Wales sites in and some of the Northern Territory sites in, because it's a stunning map showing these just tectonic framework of a continent. And we've seen it in Sinoprobe, in US Array, in OSLAMP. There is a beautiful set of information. And from a single small survey, you don't get the full grasp. You need that scales of hundreds of kilometers to be able to pick up these changes. So on my Act 2 confrontation, I'm on my first subplot here, which is what do we learn from these large arrays? What I'm going to do here is show a little bit of this project we're doing at the moment called the Curnamona Cube. Now, in the top left-hand figure, you can see a little square box on Australia, and it's surrounding, there's a blue kind of central core, which is an old craton. It's this sort of outline here on the big map. It's something like 300 kilometers by 300 kilometers. It's a Paleoproterozoic to Mesoproterozoic block. So it's an old chunk of crust that's been kind of moved around, and then bits have been added on the eastern side to accumulate Australia over the last 1 billion years. The plot here shows basically green kind of dots are long period MT, mostly OSLAMP in South Australia and New South Wales. The red dots are just geomagnetic depth sounding, and these are very much old legacy sites, almost dating back to the times when Goff and Ted Lilly, David Goff and Ted Lilly were doing these MT surveys and really identifying big conductors. So we've now got ability to be able to do very large arrays. The black dots are broadband sites, and we are gradually trying to cover the entire Curnamona Province with a much finer scale broadband MT survey. Fortunately, we couldn't cross the boundary between South Australia and New South Wales because all the borders were closed. But gradually we will fill that in over the next year. So hundreds of stations, mapping an area roughly 700 by or 500 by 500 kilometers in total. The idea is to produce a model of the Curnamona from the surface down to 300 kilometers, 300 by 300 wide. So we call this the Curnamona Cube project. What I've done here, oh, sorry, I should just give a little more bearing. This range of mountains or hills down the side, this is the Flinders Ranges on the western side. On the southern and the eastern side, this is what's known as the Barrier Ranges. And down where the pointer is at the moment is the Broken Hill lead zinc deposit, which is the largest lead zinc deposit in the world. Most of the Curnamona, though, is flat and covered in hundreds of meters of sediment, so it's had very little exploration. What I'm doing here is just showing a 3D inversion we ran with CGG's, Randy Mackey's 3D code. This is a slice 1,000 meters below the surface. You can see the northern parts of this crustal component, basically. The reds are the thicker sedimentary units as you move towards the north, and there's a very thick kind of trench of sediments and a bounding fault to the southeast. The Barrier Ranges and the Flinders Ranges are all quite electrically resistive in the top 1,000 meters, but the Curnamona is sort of, the middle part is somewhere in between. So the southern hills are resistive, but the sediments make it more conducting. If I go from 1,000 meters to 10 kilometers, an amazing thing happens. We get this enormously conductive zone, about 200 kilometers long, about 1 ohm-meter, and it maps essentially this sort of domain. These finer black lines are smaller tectonic domains as mapped by magnetics and gravity. And you can see that it sort of picks out this particular unit called the Quinyambi domain as being electrically very, very conducting. It's probably 200 kilometers north-south and about 40 kilometers east-west. Everything else is quite electrically resistive around the edge. If I go to 30 kilometers, what I've done here is plot all the copper deposits now, or copper occurrences and the copper resources. So just be bearings on these. The occurrences means that if you drill a hole and you do assays on the drill core and it comes up with even tiny amounts of copper, various sulfides and sulfates of copper. Typically, then it's called an occurrence, but it may be at a fractional amount that is not economic and way below economic. The lighter blue colors are the copper resources. So these are where they've been drilled out with a JORC compliance, which means you basically drill them out with a pattern and you work out essentially how much copper is there. And you can see that pretty much all of certainly the resources lie basically on the, this is a 30-kilometer slice of the Earth at a zone which is electrically quite conducting, so around about, well, less than 30 ohm meters. Some of these copper occurrences are really very small dispersive copper systems, so they're really hardly any connection to the basement rocks themselves. They could be entirely within the regolith themselves. So, but what we do see then is that essentially all the light blues occur in the 30-odd ohm meter or above the 30 ohm meter. So it's not a causality, but there is a correlation there between where we find copper and what we see at 30 kilometers below the surface. Conversely, where the lithosphere and the crust is resistive, so hundreds of ohm meters and above, there's no copper. So we see a system here where we can map possible areas of copper. And I particularly highlight this sort of region here. So these northern copper deposits and the southern copper deposits are separated by a gap. And there's no occurrences here and no resources because there's hundreds of meters of sediment. So undoubtedly there will be copper deposits and copper resources within this region, but they've not yet been found. Go down to 150 kilometers now. What I've done is just plot diamond occurrences down here. So where the lithosphere is most resistive, so several hundred ohm meters at 150 kilometers, we kind of see where the diamonds occur on that boundary. Australia is not a big diamond producer, and these are really very small micro diamonds, but it does indicate that there is a thickening of the lithosphere, and we see that with the resistivity. I'm just going to move south a little bit now. This is Victoria, the Victorian Gold Province, and again, this is a combination of AusLAMP, South Australia, AusLAMP Victoria, a number of broadband surveys. You can see the very dense lines of MT and the various faults and structures. You can see the Adelaide on the western side, Melbourne down on the southern side, and the continental shelf and margin down here. What I've plotted on top here are the little white circles are gold deposits, or gold mines that have produced less than 1 ton of gold, and the bigger yellow circles are where gold has been found with more than 1 ton. And I plotted the phase tensors with minimum phase, so we're indicating the Earth becoming more conducting with depth for the regions which have the redder phase tensors, and the blue show the opposite. So the blue around the coast show thick sedimentary sequences underneath which we have basement rock. So again, we've inverted these data. We've used CGG's 3D inversion code. And what I'm plotting here is just a smaller section. You can see Melbourne, the gold mining towns of Ballarat and Bendigo. This is a slice at 5 kilometers. I've also put the solid black lines. It's a bit of a mess. The white line is the coastline, and then these sort of white lines down in the south west are the 1,000, 2,000 meter contours. But the black lines are sedimentary basin thicknesses. So that's what's called the Otway Basin. You can see it's up to 10 kilometers thick. And the 3D inversion does a fabulous job at recovering the Otway Basin and also shows essentially where the gold deposits are. The crust is the most electrically resistive. To the north, we've got more conducting again. We've got what's known as the Murray Basin. If I move down to 30 kilometers now, an amazing thing happens. We see this region within the crust. I've plotted it on a scale. The red's sort of 10 to 20 ohm meters, and almost all of the gold deposits, the gold mines, particularly the big gold mines, the yellow circles, these are orogenic gold, so they're being produced by movement of fluids, and the gold is deposited along faults and fractures. They all lie above bits of the crust which have resistivity less than 20 ohm meters. If we go down 150 kilometers, I can see a sort of general trend from resistive, which is an older bit of the continent called the Delamerian origin, and the newer bit of the continent, which is called the Lachlan origin. So we do see that trend in the lithosphere. So we can map the entire scale of the lithosphere. And part of the dynamics here is that this change in depth of the lithosphere boundary gives rise to what's known as edge-driven convection. A little bit more detail. This is all these broadband sites and induction arrows, and just the contour of, in case, 13 ohm meters. And you can see pretty much all of the gold deposits, and certainly the big gold deposits, lie above the most conducting bits of the crust. So it's a phenomenal kind of correlation which we need to explain and understand, but initially, at least, it gives us a sort of a correlation, not a causality, but gives us some indication that there may be a connection in those processes. Okay, so for my second subplot, so we've established that the arrays map out particularly the lower crust, and we see the spatial correlation between copper and gold at the surface and the low resistivity parts of the lower crust. We start putting in some transects, and we put them with broadband, and we, particularly when we space them very close together, we can start looking at the connection between the lower crust and the upper crust. So I've got a couple of examples here. This is the Curnamona Province again. So my little map at the top shows the big region of the Curnamona. And you can see from this sort of red lines, there's a line of MT. It's about 130, 140 kilometers long. Broadband MT every 2 kilometers. Beautiful data, is dead quiet. There's no noise, basically. So we get excellent bandwidth. And inverted it, and we end up with this sort of series of big conductors. They're offset by what looks like faults and shear zones. One of the really compelling, interesting things was we see what looks like these conducting paths coming up to the surface in some places, this one particularly C4. But we see essentially sort of blobs of conductance, and they map beautifully to the three-dimensional inversion of the whole area. So this just provides us more, if you like, a more detailed view of the Earth, and this is down to 40-odd kilometers. These are low resistivities. So C3 is 1 ohm meter, C1 and 2 are less than 1 ohm meter. So we're looking at bits of the Earth that conduct electricity better than seawater. And I still find that an amazing phenomena that silicate rocks at 10 to 20 kilometers in the Earth over tens to hundreds of kilometers can conduct electricity as well as seawater does. Okay, so the other example I was going to show, and this is probably very familiar to many of you, this is a transect across the Stuart Shelf. This is going from along a seismic line. It crosses one of the world's largest iron oxide copper gold deposits called Olympic Dam. It crosses a few other similar systems. One's called Werder Well, another one's called Vulcan. And we took the MT, it's reasonably two-dimensional. We did 2D and 3D inversions, but these are the 2D plots. And what we find is that there's this big conducting body to the northern part of the transect at about 20 to 30 kilometers. This is our big lower crustal conductor. At the surface, we can see the regolith sediments, and they can get very thick, down to 5 kilometers in the northern part. It's a sort of failed rifted sort of region. And it thins basically around Olympic Dam to about 350 meters depth. But around Word of Well, it's about, the WW is about 500 to 600 meters. In the seismics was reprocessed for that section, and I've shown the MT and the seismics here. And you can see on the eastern side, these thick sedimentary sequences, they come out in the MT and they come out in the seismics, as we would hope they would. But what we see in the seismics are these very transparent zones, and I've marked them all down as C2 here, these conductors, and even C3 at a greater depth. The concept is that fluids moving through the earth will basically break down kind of the rock fabric to basically reset it, so it no longer has that same kind of lateral reflectivity. So we see in the reflection profiles, we see kind of breaks in that reflectivity, and they map remarkably well to the regions of low electrical resistivity, which really connect up from the deep lower crust up to the surface, and quite remarkably sort of come out at where Olympic Dam is along the middle line, a part of the array, Word of Well to the south, and roughly where Vulcan is to the north. So that was a beautiful example, but we have to bear in mind, of course, the Olympic Dam is one of the world's largest mineral systems. So if we don't see it here, where will we see it? Well, we're hoping we might see it here, and we see it some other places. So what I've got in the next slide is just a little bit of reprocessed 2021 versions of those figures. And I've used the GeoTools 2D inversion. I've kept the smoothing to be very similar between the data sets. So the figure at the top shows the Olympic Dam line, and you can sort of, it's not quite as sort of clear as the previous model. I've kind of kept the smoothing a bit more generic. But you can see these kind of finger pathways of low resistivity going from the conductor in the lower crust up to the surface, and they crop out at roughly where Olympic Dam, Word of Well, and Vulcan are. And then the figure at the bottom shows the same profile, or at least the same dimensions and scale as for the Curnamona line. And there is some quite similar type styles of feature, a lower crustal conductor, and then crustal conductors reaching the surface. Now, I don't want to draw too much into this because we're looking at different bits of crust. They have different origins, but the volcanism is almost identical in age. The potential for mineral systems of similar style is quite strong. And we believe that what we see in the Curnamona is potentially the same kind of systems we see in the Stuart Shelf. So this is a mapping. But I do want to stress that these are just structural maps. They're the architecture. So the last bit of Act 2 then is this part you can just see down the bottom. It's disaster and crisis. So all I've got here essentially is, sure, MT produces maps, MT produces models. We can integrate other geophysics into it. We can do whatever we can, but in the end, we've got architecture of varying resolutions. With the lower crust and the long periods, we can map out spatially big areas. With broadband transects, we can start to look at resolution of crust, and particularly in sort of scale lengths of pathways of a kilometer or less. And then potentially with AMT grids, what we're doing at the moment is basically looking at some of those deposits in a very small scale, kilometer scale or less, view of the last bit of the mineral system. But the crisis point is basically, what does it mean in terms of fluids, temperature, melts, metal provenances, and the preservation? Because we're looking at structures which are billions of years old. So Act 3, the last part, is resolution. And I'm going to put out a few ideas and suggestions and concepts. And I don't want to suggest that one size fits all. There are many ways that you can describe these mineral systems, and you might describe them in different locations with different tectonic regimes, different chemistries. They're not going to be a singular answer. But here's one suggestion. Something we've been looking at recently is how much carbon goes into the earth. And it's kind of, when we think about the current Glasgow conference talking about carbon as being one of the world's great issues, well, carbon has always been a major cycled element. What I've got here is a rather complex plot. It's from a paper published in 2020 in Nature, and what it's looking at is carbon that has preferentially been incorporated in marine sediments as organic carbon rather than carbonate, at the same time that oxygen is produced to produce oxidation events. So I'm just going to show the next figure, and this is called the Lomangadi-Jatuli event, and it's from about 2.3 to 2 billion years ago. This is the Great Oxidation Event. And what it means is that this went from basically having an atmosphere with almost no oxygen to basically producing quite significant amounts of oxygen. The impact of that is that the carbon that is produced from, say, biogenic materials in a very kind of low and very small sort of cellular systems are not buried as carbonates, those CO2, but they are buried as organic carbon. And the plot here is of delta carbon 13, which is the one of the isotopes of carbon, and preferentially the organic carbon increases the amount of delta 13 in carbonates. So in other words, the way to read this is that the higher the number on the Y scale, the more carbon is going into the earth. And this is a compilation of lots of data from various parts of the globe. We fitted a kind of low order kind of regression to that. It's the red line. I've also put bands of ±1 standard deviation and ±2 standard deviations. And you can see this point of time from 2.3 to 2 billion years, there was huge amounts of extra carbon going into marine sediments as organic carbon rather than as carbonates. For most of Earth history, though, it's kind of bobbed around a bit and it's kind of come and gone a little bit. There's one other region at about 500 million years, and that relates to the Cambrian Explosion and another big oxygenation event. So we've got two big oxygenation events that have happened, and at the same time that oxygen is being produced, we're getting more carbon in marine sediments. So if I just go back to this one, and I just want to highlight one aspect of this, the amount of carbon going into the ground and the amount of oxygen going into the air was from 2.3 to 2 billion years. And in this Paleoproterozoic time, this is when we're getting a very large amount of crust accumulated onto what was the Australian margin, round about between 2.2 and 1.85 billion years. So this is when these parts of Australia were part of the Nuna continent, in a completely different part of the hemisphere, and it really comprised just of the cratons of South Australia, Northern Australia, and Western Australia. And so the Curnamona was sort of at the edge of that, as is the Mount Isa block in the north and the Stuart Shelf, and down to the bottom, which is the Eyre Peninsula, in a thing called the Kalinjala Shear Zone. These are all Paleoproterozoic suture zones, and they occur somewhere between 2.2 and 1.85 billion years. And our argument here, our thesis is that these suture zones represent crushes of sediments and thickening of sediments and some subduction, which incorporated sediments with orders of magnitude more organic carbon at a very distinct point of time in their history. Okay, so what I want to do here is just map this again a little bit more onto a sort of a chemistry map of the Earth. This is some work by Gaburi and Applied Earth Sciences. It was mainly about the gold systems, but it really can be applied to any system where we're producing a kind of suturing, or we're squeezing sediments and increasing their sort of burial. So the way this framework works is, and I'll just sort of walk through it, we start off at point 1. So point 1, we might say, is where we've got sediments near the surface. They're full of organic carbon. And these are rapidly buried in about 1 million years to depths of something like 20 or so kilometers. They're relatively low temperatures. So we start off on the left-hand side at 1, and we end down at number 2 in a relatively fast amount of time. So we squash up these sediments, we thicken them to the point where we have a large accumulation of sediments, but they're still relatively cool. And they're at the sort of green schist fascist metamorphic grade. So that's a sort of, as the suturing occurs, as the collisions occur and the thickening of sediments. And we argue that in this Paleoproterozoic time, that input included a lot more carbon. The next stage is a much longer phase, but it could be hundreds of millions of years, but it could also be much more rapid if there's extra thermal input from things like plumes, or if there's, say, a break off of slab and a stenospheric upwelling. So we're basically going from 2 to 3. And what's happening there is we've still got more or less the same thickness of sediment, but we've got a sort of a thermal relaxation and an increase in temperature. And that moves the rock package from green schist to amphibolite grade. So this is round about 200 or 20 kilometers depth, equivalent pressures, but it's taking the temperatures up to sort of 500 degrees or so. At that point, organic carbon at amphibolite grade can be turned into flake graphite. So we have a mechanism here then of, particularly if we have a long period of quiescence and a sort of thermal kind of equilibrium, or if we have additional heat from plumes or additional heat from stenospheric upwelling from slab breakoff, for example, then we end up with amphibolite grade at those depths where we might precipitate out flake graphite. At the same time, those marine sediments at those temperatures, at the green schist to amphibolite grade boundary, this TGA, can release a very large amount of fluids, including lixiviants for gold, pyrite, pyrrhotite. So we get basically a source of fluids. We've got high temperatures, pipe pressures, and we release fluids that are including carbon dioxide, excipients for gold, and those are thermally buoyant fluids which can move up through the system. So we can generate essentially graphite in situ, and we can generate fluids that are lixiviants for gold and also contain fluxes of things like carbon dioxide, which can then be precipitated out in reducing environments. The final stage is perhaps the last stage, where we get erosion, we get exhumation, and so some of those, particularly the graphite, can suddenly get to much shallower depths and low temperatures, but because it's been precipitated at these amphibolite grades at number 3, we end up back on this path up to the surface here. So I'm not saying this is the only way you can generate fluids, and of course this relies on In this case, perhaps gold being part of the sediment, that in colloidal gold within the sedimentary matrix, or within the oceanic basalt from the subsurface. But it's a mechanism to drive gold and gold-bearing fluids up to the surface. If we're thinking about metals like copper, it's not clear quite where the source of those copper metals may be, but they may also come from deeper depths, being generated and increasing the pressure in this last case at the bottom here, number 3. So perhaps a plume, a refertilization, a movement of melts, magmas to increase the temperature at the base of the crust and moving that carbon-rich sediment into the sort of graphite stability field. So it's one mechanism. It's not the only mechanism, but it's a mechanism that maybe particularly we've been using to explain the orogenic golds in Victoria, in the southern part of Australia, but also may have some impact for other types of mineral systems. And it may be obviously modifications on this, and there'll be particular circumstances. So basically, this can generate a lower crustal, low resistivity, upper crustal, generally high resistivity, but from exhumation, from erosion, some of that graphite can move up. And this is what we think we see in the Curnamona Province. So moving to the climax, the end part of the story, the resolution of Act 3. In Australia, we have a number of these big conductors. They're often Paleoproterozoic. They're sort of fragmented across the country, and I've highlighted a few of these in sort of the thicker red lines. And these are based on a base map from an older inversion based mostly on geomagnetic depth sounding. So it's not a really fine-grade model of the Earth, but what we do see is essentially these fragmented bits of conductors across the country. And one suggestion and reconstruction of the continent in that time of about 2 billion years ago was essentially that boundary through the eastern side of Mount Isa, Curnamona into South Australia was a contiguous boundary. And what we're seeing here is suturing along that entire boundary as continental materials moved and accumulated. And as such, then we get higher conductivity. So finishing off, basically we see conduction in the Earth, we see spatial correlations, we see lithospheric architecture. And I think the challenge is to try and understand how that architecture and the chemistry can be connected, and how we can understand from the resistivity, how we can connect that to the chemistry. And what I've got on the bottom is we basically need more examples from where we have no mineral deposits and try and understand what we know from the endpoint deposit to understand how it might connect up to the lower crust. So my final slide is basically, we can look at it as mineral exploration can benefit from deep mapping of the crust, but we can also say that these exploration companies who find these mineral deposits are actually quite good at helping us find low resistivity regions deeper in the Earth. So I'd like to say thank you to everyone. Probably gone a little bit too far and too long, but thank you if you've stayed with me this long. And I do think there are many people who collected data over many decades by many institutions, and I would fill up the slide with all the thanks and all the people, but I think they know who they are. So do appreciate all the efforts over time, and thank everyone for their attention tonight. Okay, and back to you, Alan.
Well, thank you very much, Graham, on behalf of everybody watching and everybody who's going to be watching in the future. That's an absolutely wonderful overview of the tremendous work doing. And I really do like the bringing it back in the end to chemistry, because I often think that conductivity is more a measure of chemistry than it is of physics. You know, if you have no conductor, then it's physics, you know, pressure, temperature. But if you have a conductor, it's often chemistry. So let's open it up for questions. While we wait for them to roll in, perhaps we can have a little bit of a discussion on if you could just roll back to the Griffin et al. Right at the
yes.
beginning there. The Griffin et al. Because it's just something we should perhaps discuss a little bit about.
Yep.
There. Yeah, you had the light green as resistive and the dark green as conductive. Why did you say that?
Well, look, their model and their cross section is simply a cross section. So they basically colored the sort of refertilized the sort of I guess potentially rehydrated parts of the deep lithosphere. If in this case they've got a plume, they had some other kind of cartoon type models, and my kind of the broad scale kind of brush view of the world is that the depleted subcontinental lithospheric mantle, in most places you would expect it to be depleted and therefore basically lacking in volatiles, lacking in hydration. In that case, we expect it to be electrically resistive. Now, the sort of refertilized parts, I guess, that could be in the sense of hydration. So we introduce hydrated minerals, or we rehydrate minerals at the base of the lithosphere. Obviously, in some places, we are introducing melt. We are mobilizing potentially carbon from deeper in the earth and into a graphite stability field. There's a potential that we may be imposing electrical signals on the top, well, or low resistivity regions. And so the dark green doesn't have to be conducting, but it's probably potentially conducting. And one of the nice things which I think Stefan and Teal and I and others have been sort of looking at is that this sort of very simple kind of cartoon map, actually, if you looked at the Gawler Craton from the west to the east, would look like that. We don't necessarily, I mean, there are actually some diamonds in the middle of the Gawler Craton. On the eastern margin, this is where we're getting all the big IOCG type deposits. We potentially are seeing, you know, essentially the 1.5, 1.6 billion year old plume interaction with the lower crust and the lower lithosphere that's generated and pushed a lot of the sort of the melt and essentially then the metals up to the surface. So that this kind of cartoon version of the Earth actually kind of fits what we might see in the Gawler Craton. But look, it's not that's a bit of a broad sort of view of the world. But I'm not saying there would always be that, but there is potential to be so.
Yeah, just really just that everybody doesn't think this is the status quo or the accepted model, because from the Capval Craton, which we know is the best craton in the world that we know the water content of, we find maximum water content at around 80, 100, 120 kilometers. And we find water decreasing with depth. That's Anne Peslier's work. And so that would suggest a mid-lithospheric proton conduction conductor. And then the second thing, of course, is carbon. You know that you've got diamonds there. Well, diamonds are pretty bloody resistive, right? You know, you need it to be able to be above the graphite diamond stability field. And some of these anomalies we're finding, like in the Slave Craton and in the middle of the Trans-Hudson origin, and also in Western Superior, we find these mid-crust, mid-lithospheric anomalies that seem to have a bottom at about the graphite diamond stability field. Yeah. So, you know, I think there's certain times when, you know, you would refertilize does not necessarily mean more conducting. It depends on hydration.
Yep.
Okay, we got a question from Matthew Como. It's actually in the chat, not in the Q&A. Matthew says, one quick question regarding deposit camp regional scales. These are discussed often in terms of horizontal surface distances, at least in my industry experience. Can the concept also be applied to vertical distances? Can the vertical scale be considered equal to the horizontal scale?
Yeah, thanks for your question, Matthew. That's a terrifically good question, actually. And to sometimes, of course, these scale lengths are in the eye of the beholder as to how you want to define them. I think you're right that the vertical scale and the horizontal scale could be considered in the same kind of realm. I mean, I tend to think of regional being the lithospheric scale in that sense. So of the scale lengths of tens to hundreds of kilometers for the crustal scales, and I think those as the camp scales as being the sort of 1 to 50 odd kilometers, if you like, sort of from the nearest surface or the base of the cover down to the moho-ish type scale lengths. And then the deposit scale is essentially the upper crustal kind of scale. But from the explorer's point of view, the deposit scale is always sort of essentially how far they're going to drill. So typically top 2 kilometers at most. But yeah, it's a good question. I think these are sort of slightly archaic kind of terms because they, deposit, camp, regional, it sort of doesn't mean much to perhaps people outside of the exploration industry. I'm not sure they really serve us all that well, but I think we probably have a similar kind of view of them.
I guess also our method is such that we are sensitive to different scales at different depths because we have an integrating technique, right? So we are going to necessarily look at larger scales as we look deeper. So we're not going to see narrow pathways in the lithospheric mantle. We're going to see blobbier versions of them. So if anybody wants to speak verbally, please raise your hand and I'll allow you to talk. If there's any more follow-up, Matthew, that you'd like. Otherwise, the only other comment from Leo Fox, excellent presentation, Graham. Knowing Leo, he's very glad that you mentioned the word Phoenix.
Well, we use a whole variety of industry equipment and so on, and all are great. But thanks for your comment, Leo. Much appreciated.
Okay. Yeah, Matthew says lots of information today. Good stuff, Graham. I think.
Thank you, Matthew.
Graham, people are pondering over what you said, particularly your fabulous model. I really like the model, the carbon model. It fits in with a lot of my thinking as well. And when you look at, I've always found the slave crust to be anomalous because it's resistive. But the slave crust is some of the oldest crust in the world. It's early Archean. And so maybe the processes that was introducing conducting material were just not operating in the early to mid Archean when slave cratonic crust was formed.
Yeah, it's a really interesting point. I've been trying to ponder a little bit about how significant this kind of concept of carbon, organic carbon being into the crust as opposed to carbonates.
Right.
And I've shown here as well that there is this additional kind of peak, if you like, at the Cambrian explosion. So the conductor underneath Victoria is what's called the boundary between the Delamerian and the Lachlan origin. So it's about 530 to about 400 million years is that kind of closure and formation of the Lachlan origin. So it kind of falls at the point when those marine sediments that would have been in sort of turbiditic kind of environments would potentially have included more organic carbon. So I'm not saying that all conductors therefore will only occur when we've got extra carbon in the earth, but we do certainly in Australia. There's a lot of the Paleoproterozoic conductors, and part of the motivation for this work was that when we looked at the structure of the Curnamona type conductors, so there's sort of the one which runs roughly north-south, and then the Mount Isa type conductor, so the Carpentaria conductor that Wen Ping and Jingming and others have been looking at in Geoscience Australia. There's the cross section is not identical, but they're very similar in morphology. And one suggestion is essentially they're similar because they're part of the same system, and
Right.
they're basically connected. And it's not an outrageous thing to do because you need to connect up these old bits of crust. But it would make some sense as to why we see Paleoproterozoic conductors more than we see Neoproterozoic conductors, for example. So, perhaps it was an explanation as to why we do see some things in one place and we don't see them in others. So I can see another question in the chat.
Yeah, Matthew, let me, I've just allowed, perhaps if you like, you can actually ask your question live. I've just allowed you to talk and join the discussion.
Can you hear me?
Yes.
Yes.
Okay, great, thanks. Yeah, I wasn't sure if the mic is working here in the home office. Yeah, great talk, Graham. So I was just thinking about this Griffin model, and at least in the image which you showed, he hypothesizes that there's this deep-reaching mantle plume which seems to bring up these fluids. But maybe it's more realistic to substitute this with an edge-driven convection mechanism, which I think you alluded to. So if you have this lithospheric step, or this difference, this lateral difference where the lithosphere, or the thickness of the lithosphere changes drastically, then of course you can have this convection mechanism instead, and maybe that's more realistic in many different settings.
Yeah, look, that's a really good point, and there's, you're probably aware of some recent work by the group from Geoscience Australia and Matthew Hoggard, Matthew Hoggard, looking at sedimentary hosted copper deposits, and essentially again saying, well, we appreciate that the copper is kind of cycled within the sedimentary basin, but to give you that thermal input at the base of that sedimentary system, you need something driving it. And they were arguing that it was, again, edge-driven convection. And, I think one of the things we might try and think more about from data sets like OSLAMP is to try and think, how can we define all the lithospheric kind of thickness resistivity kind of variations to see if, mostly we're working on seismic based lithospheric models or LAB kind of constraints, but whether the resistivity will also give you something similar. But just coming back to your question then, but I agree. I think it doesn't have to be a plume. It could be, it could be a plume, but the edge-driven convection may be quite a commonplace mechanism to drive heat from deep up to shallow in a very sort of efficient manner. I think, Alan, you might be on mute, I think.
Yeah, sorry. Yeah, I was just saying thanks, Matthew, for that. And for future EMinars, we're going to try and promote active discussion like this and bring people in live. So it's 1:45 in the morning for Graham, so I think we should let him get to bed. And I'll just grab the screen back from Graham and share my screen just to remind you next week's EMinar is by Marceau Gresse on the study of the Kiyama volcano. So we've got MT, seismics, thermal imaging, and cell potential. So I hope to see everybody next week. And in the meantime, I'd like to thank Graham again for a wonderful talk. And goodbye, everybody, and stay safe.
Bye, everyone.